Assalamualaikum to lecturer Encik Ni Abdullah. Today we are going to present about Cussons 2 shaft gas turbine.
My name is Muhammad Izzat bin Shamsuddin, matrix number 10 DJL30022F 1023.
My name is Fatin Humaira binti Muazzam Shah. My matrix number is 10 DJL22F 1027.
My name is Itina Zulaika bin Hassan. My matrix number is 10 DJL22F 1025.
General specification 2.1. General gas turbine unit has been tropicalized and is generally suitable for use in ambient temperature of up to 40 Celsius and ambient condition of up to 18% relative humidity. 2.2. Gas generator. The gas generator consists of single-stage centrifugal compressor, a single gas fuel combustion chamber, and a single-stage radial turbine. The compressor impeller has a tip diameter of 72 mm, whilst the radial turbine has throat area of 16 cm and tip diameter of 17 mm. The gas generator operates at a pressure ratio of approximately 2.1 and speed range 500 to 2000 relative per second. The combustion chamber and the associated instrumentation are designed for use with the proper C3H8 but may be used with mix of proper and written C4H10 provided that the pressure in the supply bottle is sufficient to inject the fuel into the combustion chamber.
Next, I will talk about power turbine. It has 90 mm diameter, single-stage radial turbine operating over the range 170 to 600 RPS and developing a maximum power to approximately 4 kW. Next, I will tell about loading alternator with silicon diode rectifying circuit. It has 3-phase alternator with manually controlled excitation, supplying a 3-phase bridge rectifier circuit giving a variable DC output of up to 75 volts with approximately rating up to 35 ampere.
3.5. Instrumentation for both operational and experimental measurement is integrated into the color schematic diagram on the instrument and control panel. This is 6 important items in instrument. Number 1 is temperature. Number 2, pressure. Number 3 is air flow rate. 4, fuel flow rate. Number 5 is rotational speeds. And lastly is power output. 3.6. Starting system. The gas generator is started by blowing air from a centrifugal fan onto the compressor of the generator. 2 butterflies valves gauge together and operate by a start-run control from the front panel are used to close off the normal air inlet silencer connection and direct air from the fan onto the compressor.
Next, as shown at the screen, this is the data that we got from the experiment. First, pressure measurement. We got reading only up to 700 bar. As shown, gas bottle supply indicator is 1.8 bar. Combustion chamber inlet gas pressure is 0.4 bar. Combustion chamber pressure is 0.15 bar. Power turbine inlet pressure is 0.025 bar. Combustion chamber pressure loss is 0.6 bar. And lubricant oil pressure is 1.3 bar. Second, flow measurement. As shown, fuel flow is 0.4 at 0.7, meanwhile inlet flow is 104. Finally, temperature measurement. As shown, inlet air temperature is 40 degrees Celsius, compressor outlet temperature is 60 degrees Celsius, fuel inlet temperature is 41 degrees Celsius, gas generator turbine inlet temperature is 660 degrees Celsius, power turbine inlet temperature is 580 degrees Celsius, power turbine exhaust temperature is 560 degrees Celsius. Lubricating oil temperature is 680 degrees Celsius. Here is the results. After some calculation, for total expansion ratio, we got 6.25. Meanwhile, the semi-dimensional flow, we got 142.54 bar. As shown at the screen, the graph we get is a straight line, same as theory.
Question number 1 is discuss about compression process. So, I will answer about compression process. The compression process in a gas turbine like the P9005 involve drawing in ambient air, pressurizing it in multiple stages using rotating blades and increasing its temperature and density. This compressed air is then mixed with fuel and ignited in the combustion chamber to produce high pressure gas, driving the turbine blades to generate power efficiently. Question number 2 is explain about PV diagram for an ideal gas turbine cycle. Okay, the PV mean like pressure volume diagram illustrates the ideal gas turbine cycle, such as the one utilized in the P9000 units. It begins with a function for 1 to 2, then followed by constant pressure conversion 2 to 3, expansion producing works 3 to 4, and lastly exhaust 4 to 1. This cycle process efficiently converts thermal energy into mechanical works, crucial for the turbine operation.
Conclusion. Number 1. The data that was recorded consists of 3 different run engine speed: 4500 RPM, 1700 RPM, and 185 RPM. Number 2. When analyzed the Brayton cycle, the thermodynamic properties calculated to provide a complete analysis of the gas turbine engine cycle. Number 3. Throughout the experiment, there are multiple sensors in which are used to measure the pressure. The mini-lab sensor system records the inlet pressure and temperature at the compressor as P1 and T1. The following step will record the exit pressure and temperature as P2 and T2, followed by the combustion chamber pressure of P3 and turbine inlet temperature of T3. Number 4. The turbine exit pressure P4 and temperature T4 are logged along with the final value of nozzle exit pressure and temperature as P5 and T5. The Brayton thermal efficiencies for run 1, 2, and 3 we calculate to be at 0.102%, 0.677%, and 1.20%. Number 5. Moreover, the efficiency of the turbine alone was calculated to be at 85.43% amongst the first trial. We noticed that they have the capability 1% thermal efficient. In conclusion, we can also state that the components of a cycle also provide a huge factor to the overall efficiency of the cycle itself, such as if the components are less efficient, the cycle itself is going to become less efficient.